I think we can just start with a brief introduction of Considerate itself. So Considerate itself sees itself in the context of the product development and the technology readiness levels 4 to 8. Everything that's beyond technology readiness 8, we usually treat with spin-offs, with joint ventures, whatever. Our expertise lays beyond this product development in the context of machine learning, especially in the context of federated learning, in the context of electronic consensus. This is anything connected to blockchain, to self-sovereign identities, and so on and so forth. Machine-to-machine communication, especially the vehicle to anything, V2X communication. There we currently try to map it on a drone, for example, and in the context of Internet of Things. Regarding industries we operate, these are various. So usually we take our product development expertise, we take our technical expertise, and together with our customers in the branches, in these industries, we try to develop great new digital future. So now, no long words regarding Considerate. Let's just start. Let's jump right into the topic. So the problem that occurs quite frequently in the context of machine learning is that you require a lot of data. And there would be a lot of data, or the data cannot be gathered, but there would be enough data if you would take the data together with your competitors. However, no one wants to share their data with the competitors due to security concerns, for example. And obviously they don't want that the competition knows what they're doing. And that leads to the problem that machine learning projects are not realized. We thought that's not cool. So we thought, how can we solve this? And I want to explain you the solution of federated learning in the context of the example of the Google Gboard. So the Google Gboard is the keyboard you have on your Android smartphone. So for example, I write, hey, what's up? And another one writes, hey, how are you? And I type the word just, hey, and then, for example, the system has to suggest me something and it has to suggest another one something. But let's jump right into this example. In this example, Google would provide the controller. The controller generates an initial model, machine learning model. And it also provides initial parameters, which are not accurate, like the same as in any other machine learning project. The single nodes we see here are separate smartphones. And each smartphone has different data, as I just explained. So for me, it's like, hey, what's up? For someone else, it might be, hey, how are you? So each smartphone got different data. And now we shift the parameters, initial parameters from the controller to the smartphone. And each smartphone trains the model it received with its own data. And now we got 4 different models. These models, we just send back the parameters, not the data. It's just the parameters of the model. We send back to the controller. The controller merges them and sends them back to the single nodes. Each node trains them again to have this personal touch, like I have, hey, how are you? The other one, hey, what's up? That this stays the same. So the overall model improved, but the character of each smartphone received the same. So in total, the model improved for each node. This brings various advantages with it. And now I would like to hand over to my colleague Amadeus.
Thanks, Toby. Yeah, the first advantage, because we are only transferring the parameters and not the real data used to train the models, is privacy. This is pretty useful for medical diagnostics or for predicted maintenance when a lot of companies use machines by one manufacturer, and the manufacturer wants to provide some AI-based prediction when maintenance is useful, and there should no data be shared. because the runtime parameters of the machines should be kept private. Another advantage is that we basically profit from more data, for example, in burglary protection. Because in burglary protection, burglaries are hopefully pretty rare. So we have not much samples for burglary in a house when we have a security system there. But combining the data of all security systems in different houses leads to more data for cases of burglary, which lets us train better models. Then we have less traffic because we don't transmit the complete data and only the model's parameters. And this can be useful for traffic intensive applications like transferring data from the stock market and basically compressing them by using AI models. And yeah, this whole thing leads to better models, which is useful for all applications in the sector of artificial intelligence. Yeah, to integrate the federated learning in in an existing machine learning pipeline, we only go to the step where we actually train the model and insert some more steps where we import the parameter we get from the controller, train our model, export the parameter, and repeat this for a specified number of rounds. And when we're done with that, we import the final parameters we got from the coordinator, and then we can continue with validating the model and use the model. Yeah, we invented a toolbox which is capable of doing exactly that, and should be implemented in existing machine learning tasks where basically existing models can use as the input for this toolbox. We have there the basic coordination, so handling the rounds and so on. Then we have a gRPC coordination server, which takes the role of the coordinator, which we saw in the animation. We plan to do also a blockchain coordinator so that we have decentralized network. Then we have some standard aggregation stuff to bring the parameters together, and we have some advanced aggregation stuff where we implemented fault detection for supervised learning. So if there are participants which are sending corrupted data in the federated learning, we are able to take them out and don't consider their data in the aggregation step. We also implemented algorithms for unsupervised learning and are planning to implement to research about vertical federated learning, but we come to that point later on. Yeah, the implementation at the client side is pretty easy. It comes down to two methods. One method where the model is trained, where we get the import parameter and a number of epochs for training the model, and this method should return the exported parameters of our machine learning model. And the second method is to implement the final parameters after the last round is over.
All right, perfect, thank you. Now we want to dive a little deeper. We just saw the toolbox here, and there's been quite some words which might not be obvious to everyone. So now we want to dive deeper into each section, that in the end you understand the whole concept. There's a lot of machine learning at all as well, not just federated learning, but it will also always be in the context of federated learning what we explain. So Amadeus, please start to explain us, like, what is a GRPC coordination server and what is a blockchain coordinator, and what should I use for which application?
Yes, so the gRPC coordination server is basically a single node that does the coordination and the aggregation and the control at one point. So I have a server, I host it somewhere, and the participants connect to the server, transfer their parameters to the server, and receive the aggregated parameters from it. On the other side, we have a decentralized approach where we use blockchain, where we have no single node controlling the whole federated learning process. Instead of that, we want the participants to organize themselves and do the aggregation by themselves. So the advantages for using the server over blockchain are that we have more control, we have easier coordination and aggregation. The downside of this is we have a higher risk of failure because we all depend on that single node, which is the server. And if the server fails, we can't do the federated learning training. This cannot happen when we use the blockchain coordination, because there we have we don't have this single point which can fail. Therefore, the control and the coordination is much more difficult. But we also don't need a trusted third party when we have this. So we have this trusted third party as the server, and all participants need to trust the server to handle the parameters correctly and don't reverse engineer their models to get a clue about their training data and so on.
All right. Now I have a question, Amadeus. So on the one hand, there's just one red, like one downside, and on the other side, there are two red quarters. So is the one better than the other one?
No, this totally depends on the use case you're using this for. When you have like a predicted maintenance system where you basically can say that all users of the machines created by a manufacturer trust the manufacturer who hosts the server, this would be an easier solution. But if it gets more critical and you have more participants and they don't trust, they are not willing to trust a third party, the blockchain coordinator is a better solution.
All right, thank you. So now the next section we want to talk about is the difference between supervised and unsupervised learning, to understand like which algorithms we implemented already and which algorithms can be used in that context, for example. However, since I do not really know how good our audience knows like machine learning already. So we have like one part which is more easy to understand, like to understand the basics, what is the difference? And we have one part which is way deeper. So who would say, let's skip the basic explanation and let's just go straight on to the more technical and more depth part. So in case you want to skip the general difference, please raise your hand now. You can raise your hand by moving down with your mouse. Then there's some kind of a bar, assumed. Okay, it looks like everyone wants to hear the explanation. That's great, since I love the explanation. I brought you a little picture of myself being quite young. And as I've been young, someone came to me and told me, hey, Tobias, this is an apple. And another one came to me and said, hey, Tobias, this is a banana. And Tobias was a quite clever boy. And he thought, hey, if there's a red color in a round shape, it probably is an apple. And if it's a curved shape and a yellow color, it probably is a banana. But in the beginning, someone came to him and said, this is an apple and this is a banana. Now, Toby grew up and he saw books. And he saw there are good books and there are bad books. However, he didn't know the names. He couldn't name them as comic and as fluent textbooks, for example. This is the difference. So in supervised learning, someone comes and tells you, this is that. This category is called that name. In unsupervised learning, the goal is to figure out which categories are there, but we don't know the name of the category in the end. When we have categories, where we want to have names and we need to put names on, this is called labeling in the context. And now we go deeper in the tech. We got a quite filled slide. So here I want to hand over to Amadeus. Whoever is totally new to this topic might can grab another coffee, for example, or just listen. Amadeus, the stage is yours.
Thanks. So here are the algorithms and techniques we implemented so far. Yeah, so for the parameterized models, which are neural networks, the k-means algorithm, naive Bayes, and so on, this is mainly for the supervised learning models. We have different aggregation algorithms where we can take the parameters and make a global parameter out of that. So we have the basic aggregation, we have weighted aggregation where we can basically weight these parameters by number of samples or so on. Then we have robust and selecting aggregation, which is useful for handling outliers, or if participants send corrupted data, we can filter them out. And then we have the changing aggregation, which is useful for building pipelines. For example, if we want to do, first of all, some federated normalization and then do some federated training. Then we implemented some more complex algorithms where we don't just get away with aggregating the parameters. This is, for example, FedN. It's a normalization algorithm to normalize data on decentralized data sets with regard to the cumulated data, but we don't want to share any of these nodes, and this can be done by this algorithm. And then we have two algorithms for unsupervised learning. So unsupervised learning is a little more difficult because most of the common algorithms are not parameterized, so we can't do basic aggregation or general parameter aggregation to use them for federated learning. At the first one, we used the centroid-based clustering. This is the algorithm called federated clustering gradient descent. This is a variant of k-means, which is the only parameterized clustering algorithm I know. And this is optimized for federated learning. So it uses only 10% of the participants per round, and it performs better than just aggregating the means of k-means. And yeah, it performs better with regard to the whole data set. Another algorithm is called federated density clustering. It's a federated density core. It's a density-based clustering algorithm similar to dbScan. So someone of you might know dbScan. And this is a not parameterized algorithm at all. So we figured out a way to reduce the data to its core points and do some aggregation for this core points.
All right, thank you. So now we come to the next thing, which I think 95% of all the machine learning consultants are not able to differentiate. What is the difference between horizontal, vertical, and transfer learning? And I think we just brought you a quite good explanation, which we just hear by Amadeus in a minute. However, all the federated learning stuff which exists so far, so either at Consider It or somewhere else, is only related to horizontal learning. So you can see later on the capacity, what is free as well. Amadeus, please go ahead and explain us what's the difference.
Yeah, so on this sketch, we have on the y-axis our features and on the x-axis the identities. So identities are real-world objects. And when we extract features from that, we get our samples. So here we have, to stick to the banana and apple example, we have these both identities, and we have the color and the shape as features we extract. So then we see a red, blue, and a green rectangle, which is representing the data used for different models. So we have a red model, a blue model, a green model. The red model uses more the shape of the object and has seen a lot of bananas and just a few apples, for example. The blue model has seen a nearly equal amount of bananas and apples and uses more of the color. And the green has only seen apples, but uses shape and color as features. So when we now take the overlap of the data where the features are the same, we are left with this horizontal bar. And because it's horizontal, we call this horizontal learning. There we can create one parameter, one model with a single feature vector as input. We don't need different features because we don't have different models, and train this on the whole data set in this horizontal bar. We can also do this by grouping the overlaps by the identities, and then we are left with the vertical bar, so vertical learning occurs. There is the goal to have different models using different features and somehow combining the knowledge stored in these models by knowing that they are working on the same identities. So in this case, I know the outcome always will be an apple, and therefore I hope to find a way to combine these models, these three models, to transfer some knowledge. And if we think a step further and combine the vertical and the horizontal bar, we are able to manage the whole set of data, which is then transfer learning. We know how to combine different models, and we have seen all identities. And we basically transfer the knowledge which is stored somewhere in one model to the other models. And this is a pretty big challenge, which might be solved in the future.
All right,
yeah.
Thank you, Amadeus. Let's proceed with that one.
Yeah, so this is a conclusion in textual form of what I just said. So horizontal learning is the current state of federated learning. It focuses on data with same features, and we train one model from the decentralized data. In vertical learning, we have individual models per participant designed for its feature space. We try to join the models and improve them, and we make use of the fact that they are working on the same identities. And in transfer learning, we basically combine these both horizontal and vertical learning. We have also individual models per participant. We know how to join the models. And this enables us to use the full data set or the full data space. And to conclude it in one sentence, we try to find the areas where the knowledge is in our model and to transfer this knowledge to other participant models.
All right, thank you. So now there's time to say that we're still looking for application partners. So our toolbox is currently in the beta phase. We still look for partners which apply this. This might be if you are a machine learning consultant and you want to expand your offering for your customers. We can have a small chat, or even if you have no clue about federated machine learning or machine learning itself, just connect with us. We have partners. We can do the machine learning part as well. We can just apply it for you. Why would you do it? It's way cheaper than waiting till the product is in the productive version. You have the chance to influence which parts of the toolbox we develop next. And you have the insight in the cutting edge technologies with expert of federated machine learning. That's it. And now I want to thank you for your attention and ask for your questions.
Yeah, you can put questions either in the chat, or you can unmute yourself and ask questions in verbal way.
Yes. So can you conclude again the main benefits of federated learning compared to the normal machine learning?
Amadeus, would you like to?
Yeah, so this is the slide which shows our benefits. It's first of all the privacy, which is privacy by design, because we all need to, we are transferring only parameters, and we get more data. And in federated machine learning, we have the same results as collecting the data in a central point and then training one model. But doing the federated steps, we only need to transfer the parameters and not the whole data, which leads to more privacy and less traffic.
Okay. As we do not seem to have more questions, thank you, Tobias. Thank you, Amadeus, for this insightful presentation. And to the rest, hope to hear you soon at one of the next webinars. Thank you. Bye-bye.
All right.
Have a nice evening. Bye-bye.
Bye.